we need to do hypothesis test. Now we're getting, as the final thing in our university class, we get to the Chi-square test, which is high school stuff level B. I'm sorry. We see it in a slightly more general version here than the high school version. But now you're also skilled in p-values and hypothesis testing, so it should be a piece of cake for you. We could have had this lecture a few weeks ago, but for many other reasons, we have it as the last lecture here. Anyway, so relax and enjoy. We want to compare. Not only two proportions, but potentially C proportions. Look, remember our health malformations data? It was like 10 different years, so 10 different proportions. We might want to hypothesize to investigate, could those 10 proportions from year to year actually have been produced in a world where the real underlying risk proportion had been the same all along? So the apparent increase we see, is that really an increase or is it pure noise? That's the question we're asking. These are important questions for where to throw all the billions of our society, right? Should we throw a few billions at this to find out why? Or should we just say this is random noise? Let's spend our billions for something more relevant. We only have so many billions. So the numbers come here. So remember my blood cloth example there? I had two proportions. Now I have C proportions. C samples. In Danish sometimes C becomes K, but let's use C for a number of columns also. Yeah, well, what's the approach to compare those proportions? Now we are going to reason, we're going to set up a hypothesis test statistic that in a nice way measures whether these proportions seems to be the same or they appear to be different. That's the statistic that we will define now. First of all, to get at this comparison, we do this joint number first. So I count, if it was the malformations, I would count all the babies over 10 years that had malformations, and I would divide by the total number of births across all the 10 years to get the joint estimate. We saw it on the picture also in the report. It was the flat one right in the middle. That's the overall joint percentage. I start out by computing that one. That's the one that should sort of, each individual year, each individual proportion should be pretty close to this one if they're the same, right? Or if it's far away, it indicates that they're different. Let's see how we make that reasoning and the way we compute this comparison. I repeat again, I use this joint p hat across all groups. I take this p hat and I go to each n. We don't have exactly the same number of births. I used the wrong number. We have in the order of 60, 70,000 number of births in Denmark each year. I divided by 2. It's 60, 70,000 of births in Denmark each year, but it's not exactly the same, right? It's different from year to year, and that's fine. It can be different for this. It doesn't have to be the same. I go with my proportion. I compare with the number of births from this year. And I say, to match the common proportion, I know that this exactly, if the common proportion, say, would be 5%, I say the expected number of births this year to match the hypothesis of everything being the same should be this number. This is E1J, the expected number of births in group J or in year J. So I compute what it's supposed to be. What's the expected one if they should all be the same? And then I can also, of course, compute that's just 1 minus that number. If I have the expected number of malformations here, the other number is the expected number of OKs, right? So these two add up to the NJ. I compute that for each year. These are, and then I have a data table. That's how we should think about it now. we construct what we call the expected data table. I have my observed data table, then I construct the expected data table, which is exactly how the numbers should look like to match exactly the hypothesis. I construct how they should look like. And then what do? I compare the expected table with the observed table. And by that comparison, I get a measure of how far away from the hypothesis are my data as a whole. Kind of an indirect way, a bit like the F-test construction in analysis of variance. It's a similar line of thinking here, actually. There is a rule of thumb that makes this reasoning here, how to compute the expected values. This is something, I mean, you'll see how to do it in R, but you have to know how to do it yourself. If you check old exams, you'll see sometimes you're asked, how do you compute the expected value? So you have to think about how this table is found. That's the way to find the test statistic that we need to find here. We need to be able to construct this table of expected values. Now, we don't have to use our brains each time. There is a rule of thumb that makes it easy to find expected values that in a way takes these formulas and put them into this general. It's namely a very general form that we can use on all sorts of tables. In the next 20 minutes we'll be looking at that. When let's see, if I go back to my, let's just look at this one. I'm just gonna illustrate this formula. Let's go, here we have 58 and 166, right? It's very difficult to add numbers when you're in my position here, but let me know if I'm wrong. If I should find, I need to find, in this case, 4 expected numbers. If I'm going to do this test statistic that I'll show you in a second, I need to construct this table of expected values. It's a 2x2 table, just like this one. How do I construct it, if I should construct it manually? To construct the expected value E11, I take the row total times the column total divided by the number which is not here yet. Whoa. The total, right? If I take 57 times 58 divided by 224, that gives me the expected value. This is just the rule of thumb that puts this thing into play. It's the same thing. It's not a different thing. It's just something that is easy to remember, not so easy to understand why you should do exactly that, but it's easy to remember when you have it, right? You take so in a general table, this goes for all sorts of tables actually, as I already warned about. In any such tables, N by, and we're going to see R by C tables in a second, any number of categories and any number of groups actually, we can find the expected table by multiplying row total by column total and divided by the overall total. That goes for all. You combine them all and you have the E table. That's the way to do it by hand. The way to understand what it means are these ones. The other one is to find them rapidly. Having found the table of observed numbers, having found the table of expected numbers, we were given the table of observed numbers in the first place. We find the table of expected numbers that matches exactly that the proportions should be the same, right? The idealized outcome with the same proportion. The E table, for the E table, all the proportions are the same. That's a data table with the same totals as the original table, but with numbers that matches exactly the common proportion. Then we compare the two. Now I'm still talking about I'm talking about proportions with only 2 possible outcomes just until 10 minutes from now. But then there could be any number of groups to be compared. The C could be 2, then I have a 2 by 2 table, right? Or the C could be 10, like in the malformations data. It works for any number of proportions. We compare the observed table with the expected table by this formula. We subtract them from each other, we square them, and we see it relative to the expected. That makes sense. A deviation of 10 is a huge deviation if the expected outcome is 2 or 3, but a deviation of 10 is a small deviation if the expected outcome would be 1,000. So it's not a proof of anything, it just kind of makes the point that it makes sort of sense to see it relative to the expected outcome. Having done this, this is a comparison. If the observed numbers match exactly the expected numbers, this becomes a very small value altogether, right? If they don't match, it becomes a large value. Somewhere there is a limit between signal and noise here. The way to make the distinction, the theory people tell us, if I do this comparison of proportions in a situation where the proportions are truly the same, that is, I assume the null hypothesis is true, then the sampling distribution from time to time that I do such a thing, this thing that I computed follows a chi-square distribution magically. We've seen the distribution before. That is the right way to distinguish between signal and noise for this particular setting. That's what statistical theory tells us. So we can use the chi-square distribution with the right number of degrees of freedom, which is number of columns, number of groups, number of proportions, -1. And if our observed one is much larger, or I should say larger than the critical level of this distribution, we reject the null, saying that all the proportions are the same. We have one of those particular conditions of this lecture 12, that our method doesn't work for all cases. It doesn't work if the amount of data, if the n's are too small. In this case, this requirement is expressed like the following. When I have found the expected tables, none of the expected values should be smaller than 5. They should all be at least 5 for this to be a valid approach. Otherwise, you don't have an approach. So, well, we already discussed it a little bit. Here was the 2 by 2 table. When I'm going to construct the expected table, I sort of repeat my table with the totals, but without any content. And then I start, let me just check how. For instance, to get the E22, now I'm positioned myself here, right? I'm here now. So I go and take this row total, this column total, and divide by the total, right? That's what I've done up here. And then I do that, then I do this 4 times. Or I start subtracting and checking. There are some restrictions. But anyway, we could apply this 4 times. Having all these 4 expected numbers, I compare them with the observed numbers, square them relative to the expected numbers. There are 4 of them. Always remember to include all the elements. It's a classic mistake to only take half of them because you think, no, it's a proportion, so I only need half of it. No, for the theory and for everything to work, when you have a 2 by 2 table, it's 4 pieces, 4 items in finding this chi-square statistic. It becomes 8 this time. The critical value, it's a 2 by 2 table, or there are 2 proportions to be compared. So following what I told you, the degrees of freedom would be 1, right? C minus 1, C is 2 here. This is number 2 on our list of, not because it's important, it's the number 1 squared. I forget about this. Irrelevant information right now. The point is, how large should such a chi-square test statistic be for such proportion to be statistically different? Well, it should be more than 3.84. Are they different here? Is the health risk different between those two groups in this case? Yes. The observed proportion was also pretty different, right? 40%, 21%. And now we have confirmed that it's not only due to random fluctuation, it's actually a real statistically significant difference that we see here. We could find the p-value also by the chi-square. Probably I didn't bring that. Anyway, let's game you. Okay, your short-term memory is okay. That was just what I was talking about, right? Actually, this number is exactly the chi-square coming from my example, my example from before, the 65% compared with 55% out of 500 in each group. That's the one that I talked about before. That actually gives a chi-square of 10, if you compare those two, which is, as we've learned by now, really strongly significant because it's way beyond the critical value of 3.84. So yes, they are definitely different. Are they statistically different? Yes, they are, because the observed test statistics is way larger than the critical value. Still the music guy on the top.